so let's go ahead and get started with the digital logic practice problems. So first one, go ahead, write down your answer, discuss the answers with your group, hear your questions. So go ahead, answer your questions first on your own, then discuss them with your partner. Okay, so first question, why does sequential logic need a clock signal and combinational logic doesn't? Well, let's take a look at what they do. So in combinational logic, the clock signal tells the circuit when to update, that is, store the values or the state. So remember, we have this picture, we have this memory or this flip-flop or this latch, which stores something in it, has an input and output and a clock signal. And when the clock signal comes in, it takes whatever's on the input and it stores it so that it goes to the output. So that's what the combinational logic does. Sorry, what the sequential logic does. The combinational logic is different. It always changes its outputs whenever the inputs change. So combinational logic is just a whole bunch of different gates, and you put in an input, they go through some logic, and right away an output comes out. But it changes immediately when you change the inputs, the output changes. So this doesn't have any sort of clock because it changes immediately whenever the inputs change. But for sequential logic, it only changes when the clock comes through. And what that allows you to do is allows you to build circuits where you can compute something and then you can remember it on the clock signal to use it again. This is particularly useful if you want to feed back. So remember this picture here? Looked an awful lot like a counter we had. Okay, what are the differences between SRAM and DRAM? Well, SRAM uses powered or active transistors to store value through feedback. This makes it large and expensive. Remember, this is what the SRAM circuit looked like. It had one inverter and another inverter, and they would send the signals back and forth and around in a loop. But both of these inverters were plugged in. That is, they got power from the circuit. That's how they could regenerate the signals. But because they could regenerate the signals, they could send them out with a lot of power. If they send it out with a lot of power, that means you can make it quickly. So because you have more power, more current going out here, you can drive current out here onto the output wire. And even if it's a really long wire, you can change its voltage pretty quickly, which allows you to get fast output. DRAM is different. It uses passive, excuse me, unpowered capacitors to store the value. So here you are, DRAM just has a small capacitor, and that's much smaller than having these transistors. It doesn't need to have power, but you can only put a little bit of energy in here, only a few electrons. So those electrons both dissipate over time, and when you connect it to the output wire, these few electrons have to go on the output wire to change the voltage. And it takes a while because there aren't so many electrons. It takes time to detect it. So DRAM, because it's passive and uses capacitors, can be very small and cheap, but it's slow. SRAM, because it uses these active transistors, is much larger, but it can also be much faster. All right, so here's a question on truth tables. Go ahead, pause the video, answer the question on your own first, then discuss it with your partner. All right, so how many rows and columns will a truth table for the following circuit have? 3 inputs and 2 outputs. So here's an example of this sort of a circuit. So we've got 3 inputs, A, B, and C, which go into the circuit, and 2 outputs, E and D. So if we take a look at this, the truth table is going to go through all the possible combinations a circuit can do. So we have 3 inputs, so 2 to the 3 are 8 possible input combinations. So that means we're going to have 8 rows here. So we're also going to have 2 outputs. So this is, sorry, here's our 3 inputs and our 2 outputs. So my apologies. For all 3 of the inputs, we have all the possible combinations here, and we show the outputs for all of those. So we have 5 columns, 1 for each of the inputs, 1 for each of the outputs, along with 8 rows, where each row has 1 possible combination of the inputs. Okay, so go ahead and practice filling in the truth table for this 4 input AND gate. All right, so what does this look like? Well, so an AND gate is only true when all of the inputs are true. So if we look at the truth table here are all our inputs and all the possible combinations. The only time the output is going to be true is when all of the inputs are true. So 1, 1, 1, 1, and you get a 1 here. All the other combinations are going to be false. 0 is your output because they're not true. The AND of these is not true. All right, go ahead and fill out the truth table for this circuit. All right, so here's the truth table for this circuit. How do we get it? Well, let's take a look at the first input, the first gate here. So this is an AND gate. So it's saying A and B, and that gives us the value E as the output here. So A and B are true here, where A and B are both 1. So E is going to be true. And here, where A and B are both 1, and E is true. So we can see that for all the possible combinations of A and B, only the ones where they're both 1 is E going to be true. All the rest of the time, E is going to be 0. Now let's take a look at D. So D is E or C. So for the E part here, when is E true? So D is going to be true if either one of its inputs are true because it's an OR. When is this input E true? Well, it's true here and here. So the output D is going to be true when E is true in both of these cases. But this is also true whenever C is true. So or when C is true. So where is C true? Well, C is true in all of these cases. So that means that the output is also going to be true in all of those cases. All right, let's go ahead and do it the other way around. Here's a truth table. Practice figuring out what the logic function for this truth table is. Okay, so let's take a look at this. So where is the output Q true? Well, it's true here. And what is this? This is not A, because A is false, and B. So when A is false and B is true, Q is true. So not A and B, that's that row there. And here's this other row. So this row is when A is true and B is true, then Q is true. So what's the logic equation? Well, it's either one of these. If either one of these are true, Q is true. So it's not A and B, or not A and B. Now, if you look at this a little carefully, you can see there are two terms here. They both need B to be true. One of them needs A to be false, and the other needs A to be true. So this is saying either combination of A and B is there. So we can simplify this. This is just Q equals B. And if you look down at the circuit here, you can see that whenever B is true, Q is true. All right, go ahead, pause the video, answer this question first on your own, then discuss it with your partner. Okay. Which of the following logic blocks have to convert between binary and one-hot? So remember, one-hot encoding means you have a bunch of wires, but only one of them is true at a time, and the one that's true indicates the value. So if the second wire is true, it might be a 2. If the third wire is true, it may be a 4, that sort of thing. Binary means you have a binary encoding using the wires. So let's take a look at these. So what does a mux do? Well, a mux takes in a whole bunch of inputs and selects one of them. And the select here on the mux is binary. So you put in a binary value here and it chooses one of these inputs to it. So this is a binary select input. So this is definitely have a binary to one-hot converter inside. How about a demux? Well, a demux does the opposite. It takes in one value and then sends it to multiple possible outputs. And again, you have a binary select here. So this binary select is going to choose which one of those are. Now we have an encoder. Well, an encoder takes a one-hot signal and converts it to binary. So it's certainly going to convert between binary and one-hot. And a decoder, well, it does the opposite. It takes in a binary signal and converts it to a one-hot signal. So this is certainly going to take a binary input and convert it to a one-hot output. So all of these here are certainly doing conversions between binary and one-hot. How about an adder? Well, what does an adder take in it? It takes in an A and a B and a sum, and it generates a carry. Sorry, it takes in A and B and generates a sum and a carry out. There's no binary to one-hot encoding converting going on there. And even when you put a whole bunch of them together, you're just propagating the carry along to the other terms. So this doesn't have any binary to one-hot conversions in it. Okay, now we're going to go ahead and do a practice here. So we've got the following circuit set up here, and your job is to figure out what the output looks like for these inputs and describe what this block does. Now, go ahead, pause the video and try and answer the question. And if you get stuck, go ahead and unpause the video and I'll give you a hint. Okay, so here's a hint. I hope you've tried to solve the problem first before we give you the hint. Let's take a look at what's going on here. So imagine I put the following input in here, 1, 0, 0, 0 on these inputs here. What is the encoder going to do? So the encoder is going to take this one-hot input and convert it to what? So what are the outputs going to be here? Now, when the encoder converts the one-hot input to something else, that same something else goes into the input of the decoder. What does the decoder do if it gets that same input here? What's its output going to be? So think about this chain from this conversion going back and forth. Now think about up here with the least significant bit. So we put a 1 up here, and it goes into this demux. So what is the demux going to do? Well, it's going to put that 1 onto one of these wires. What controls which wire it goes on? So which one of these wires is going to be true? Now think about the mux over here. What are the inputs to the mux, and what controls which one of these inputs is selected by the mux? And the result, what do you get out the other end? So think about those conversions if you didn't get it earlier. Don't forget to double check the last one. There's something a little fun about it. All right, so let's go ahead and walk through this one. Let's take the first example here, and we're going to see what it does. Now the circuit down here, this encoder is going to take the one hot input and convert it to binary. And the decoder is going to convert binary to one hot. So we went one hot, binary, binary, one hot. So this output here should be the same as the input. The circuit here isn't going to do anything different. It's just changing how the value is encoded. Now what about up here? Well, this demux is going to take whatever values here and it's going to send it to one of those 4 wires. Then the mux is going to take the same wire and send it to the output. So this is going to take a value, go through, choose a wire, and come out the other end. So this output is going to be the same as the input again. Now let's walk through the first one of these. Here are inputs and outputs. So we put in 1, 0, 0, 0, and we put in 1 over here. Now the output is 1 hot, so this is a 3. So it's going to be a binary 1, 1. So we have input 3 is true, and so we encode 3, we get a binary 1, 1. So we're going to have 1, 1 going out on these wires. Now, this 1, 1 going out on these wires is going to send it over to the demux here, and the demux is going to say, send this to output 3. So now this 1 is going to go to output 3. This 1, 1 that's on the wires also goes over here, and it goes to the mux. And the mux is going to take output 3. So now we take that 1, we put it at the output, so we get a 1 that passes through. Same as the input, as we saw before. Now what happens down here? Well, we've got 1, 1 coming into our decoder, so that's a binary 1, 1, so it's going to be decoded as a 1 hot 1, 0, 0. So we get the same output. So what's the answer to here? We put in that value, we get out the same value. Same for this one. Let's take a look at the next one over here. So for this one here, we had 0, 0, 1, and 1 is the inputs. This is a 1 hot 0, so that's going to be encoded as 0, 0 here. 0, 0 is going to send the output to output 0. Get a 1 going across there. We have the same 0, 0 coming along these wires. It goes into the mux. The mux is going to select the 0th wire up here, so we get a 1 going out the other end. Same as the output. Similarly here, we've got 0, 0 coming into the decoder. This is a 0, 0 in binary, so we convert it to 1 hot, which is going to be 0, 0, 1. And again, we get the same output as the input. So same value here, and again, we'll get the same value here. Now, what happens with the last one? Here's our inputs. What happens here? This is not a valid 1 hot value. So this encoder requires that only one of its values is true at a given time to be 1 hot. This isn't, so we have no idea what the output's going to be. We know it's going to be some combination of 1 and 0, but we don't know which one it is. Now, if you look at what happens on the demux here, the demux, we don't know which one of these it's going to choose, but it's going to choose one of them. And the mux is going to choose the same one. So they get the same inputs to control them. So they're both going to choose the same one, but we don't know which one it is. So this 0 is going to go on one of these wires and come out the other end. So we're going to get the same value over here. But what happens down here? Well, something came into here, and it's not going to do a encoding that we know what that encoding is because it wasn't 1 hot, but we're going to get some combinations of 1s and 0s here. So that some combination of 1s and 0s is going to go into the decoder, and it is going to activate one of these. So one of these is going to be 1 hot, but we don't know which one. So we're going to get an output which is one of these being true, but we don't know which one, followed by 0 for that one. So another question, what does this block here do? Well, the output is the same as the inputs as long as these values are 1 hot. If they're not 1 hot, then we don't know what's happening. All right, let's do a question about state. So go ahead, answer the question on your own first, then discuss it with your partner. Okay, so the question here, what do the parts in the circuit need to do to make a counter? So remember a counter, we're going to store the value in the latch, and we're going to have our next state logic, which adds 1 to it. So this is going to be an adder, it's combinational logic, and we're going to add 1. So we're going to take 1, and we're going to add it to the current value. So the current value is coming out of our latch, going into the adder, we add 1, and so then we get the next value coming out of that. And then we store that in here on the clock. So in every clock signal, we take the current count, we move it over to the next one, and this goes through here, and we calculate the next one, and that counts up. All right, go ahead, take a look at this latch here, and work out the answer together with your partner. Okay, let's take a look at what's going on here. So we have a latch, and we have an input, and the input goes into this latch when not clock is true. So if clock is 0, this is going to be closed, and the input will come in. Similarly, we have a second latch here, which also has not clock. So when clock is false, or 0, it will move through here. So let's take a look at the first case here. So clock is 0. So we have a 0 coming in. It's going to go through the gate here, and it's going to get stuck in the latch. It's going to be stored there. It's going to come out. It's going to go through the next one here because clock is 0, and it's going to come out the other end. So we get a 0 in and we get a 0 out. Now we change to a 1 in. Well, the 1 is going to do the same thing. It's going to go all the way through and get stored because clock is 0. Now we set clock to 1. When clock is set to 1, this is going to open, so the signal won't get through. So now we've got a 1 here. It doesn't go through, but that's okay because this latch still has a 1 and it's outputting a 1. But this one is not going to be open. It's not going to be closed either. So it's not going to go through here, and we still got the latch outputting a 1. So when clock went 1, we don't change anything. Now we change our input to 0. What happens there? Well, again, it doesn't go in because this gate here is open, so the signal can't get in. So we keep our 1 in there, keeps outputting it, but the first one doesn't do anything because it's not connected, but the second one outputs it. So what is this design doing? Well, this is a transparent latch. When clock is 0, the signal goes through, and when clock changes, it remembers the signal. But it's slower because now for the signal to get all the way through here, it has to go first through this logic and then through this logic. So there's no benefit of having 2 of these together. Remember, when we talked about flip-flops, we had clock and not clock on one of these so that it would go in when the clock changes. That's why we had 2, but here they're using the same signal. All right, let's take a look at De Morgan's law. So De Morgan's law says that not A or B is the same thing as not A and B. So here you've got the truth tables for 2 gates, and you've got your A and B, so go ahead and prove that this is the case. Okay, let's walk through this one. So here we got A and B, and the first part we're going to do is A or B. So here's A or B. We just take this, and it's true whenever either one of those is true. Now we're going to invert it. So if we invert this here, we end up with the following: 1, 0, 0, because this was 0, 1, 1, 1. Okay, so that's not A or B. And now we want to show that that's the same as not A or and not B. So what's not A and not B? Well, here's not A. If this was A, that's not A. And here's not B. Now, what do we get when we AND these together? Well, we AND them together to only be true when both are true. So it's just going to be this top one here. So here we go. Not A and not B is 1. And we can see that not A or B is the same as not A and not B. So we proved that it works. All right, let's practice a Karnaugh map. So use a Karnaugh map to figure out what the logic function that we have here is. Okay, how do we do this? So remember Karnaugh map, we put the inputs across the top and bottom. So here's B, 0, 1, and here's A, 0, 1. Now we fill it in. So B and A are both 0. So here's B and A both 0. We fill in a 1. And so we read off the table and we fill it in. Now the next step with the Karnaugh map is to circle the largest power of 2 set that we can. And so that's going to be this one up here. So if we circle this one here, the question is, what is this logic function? Well, this line here is true when A is false. So whenever A is false, everything in that row is true. So this is C equals not A. So that's a logic function. If we go back here, we can say, hey, when A is 0, C is 1. And when A is 1, C is 0. So it is C equals not A. Let's take a look at a larger Karnaugh map. Go ahead with your partner and solve the problem. Okay. So here's the Karnaugh map. And if you'll notice, it's not in the regular order. So it goes 0, 0, 0, 1, 1, 1, 1, 0. Whereas binary counting would have the 1, 0 first. And the reason we do this is because it means only 1 bit changes between each of those, which means we can draw circles around them. If we didn't have it that way, you'd have 2 bits changing here, and then you couldn't circle them into the same function. So here we are. We filled this in. We've got A and B on the top and CI, carry in on the bottom here. So let's figure out the logic function is here. We want to circle the largest power of 2 blocks we can. So we can circle this one down here. And what's the value for this one here? Well, this is true when CI is true. It's on that row. And A is true. You see there's a 1 here and a 1 here. So this is carry in and A. This one over here is true in this column. So this column is A and B. And then finally, we've got this one over here. This one is going to be true carry in because it's in this row. And then B. So here's B is 1 and 1. Now, we circled this one right here a bunch of times, and that's fine because we're going to see output is true when any of these are true. So that's okay if they're all true at the same time. So that says that our output is CI and B, or A and B, or carry in and A. So that's the logic function. Now, could we have selected them like this? These are all powers of 2. And the answer is yes, you absolutely could have, but you end up with a more complicated expression. So this one is still A and B, but now this one here is carry in and A and not B. And this one over here is carry in and B, sorry, not A and B. And so this gives you a much more complicated expression, and that's why you want to select the largest chunks you can so that you simplify your logic equation. All right, so here are 2 extra questions. Go ahead, pause the video, try and answer them first on your own, then you can discuss them with your partner. Remember, these are extra. Okay, what would happen if you built a counter circuit without a state memory? Well, if you did that, you'd have this circuit where you have the logic going around and around. And so imagine an adder where it just has its input as its output in 1. It would just flip as quickly as it can, and you wouldn't get any reasonable values. They'd be all mixed up depending on how fast the different parts of the adder were. All right, so what limits the speed of a sequential circuit? Well, it's the slowest path through the whole circuit. So you have to figure out what the slowest way that logic can get through all the combinational logic to get to the state element, and that's what you have to do as the slowest path. If you pick a shorter path, which is faster, then if you ever need that slow path, it won't have time to finish and your circuit won't work for those parts. All right, so let's go ahead and do the reflection questions. So go ahead and answer the 3 questions about what was most interesting, boring, and what you don't quite understand from the logic module. And now go ahead and swap your answers to question 3 and help your partner with this. Try and identify a different way of thinking about the topic that can help your partner and see what your partner had for you. When you're done with that, you're all set. Thank you.